Well, here's a little video that focuses on comparing electric dipoles with magnetic dipoles. Now, I have a whole video just on electric dipoles, so this is going to be a quick summary of that. Then I'm going to compare them with magnetic. But I guess there's kind of two things you can ask about dipoles. First of all, what are they? And second of all, what do they do? Like, what makes them interesting? So I think the answer to the first question is essentially, if you have two charged particles of equal and opposite sign, then you have an electric dipole. As long as they're fairly close together, we consider them a dipole. And so we have this kind of interesting electric field line arrangement around them, and that's what's drawn here on the left. Sometimes you'll be asked for how strong the electric field is at a particular place. So the equations that I'm going to describe here really only work when you're a pretty good distance away from the dipole relative to how big the dipole is itself. So when we describe a dipole, we talk about the separation between the two charges, and that's known as S, and then the charge of each one, that's Q, positive and negative Q. And so that's a property of the dipole, and it's known as the electric dipole moment, and it's just equal to Q times S. And it has a direction that goes from the negative particle towards the positive particle. So in this configuration here, it would be leftward. But of course they can turn in different directions. So I'll just say for this one it's leftward. Now the equations that you might need to use are, first of all, if you're on the axis of the dipole itself, but a fair distance away. Now I can't really, on this figure, I don't have enough space to get a good distance away. I'd need to be farther than this. Then the electric field there can be written as 2K QS over R cubed, where R is the distance away from the center of the dipole. That's an interesting relationship, an R cubed. You tend to think of point charges as R squared. Well, these are not point charges. These are 2-point charges together that together are electrically neutral. So we shouldn't be surprised that they diminish pretty rapidly as we get far away from them. And a lot of times this QS in the equation is written just as P, the dipole moment vector. And if you're on the bisector like this, maybe up here, then the field is very similar, but it's actually half as strong. So you just get rid of the 2, and you have the electric field on the bisector as K QS over R cubed. And the direction, of course, would depend on which side of the bisector you're on, or which side of the charges that you're on. So that's kind of what they are. So they have an electric field, and we can calculate what that electric field is at a few select locations. And if you're not on one of those two particular axes, then I guess you could just use brute force and figure out how far you are from each charge and use the idea of superposition. Just add together the effect of each one. That's rarely asked, but you could do that. So I'm going to move this out of the way. So now, the next question is, what do dipoles do? Well, what they do most interesting is when we put them in another electric field. So we often take them, let's say, between the plates of a parallel plate capacitor, and we put them in there in some orientation. So the capacitor has its own field. That would be indicated here on the figure on the right as the parallel horizontal lines. And then we've got the dipole that's placed in. So if you think about what happens to any charge when we put it in an electric field is it will feel a force. And positive charges will feel a force that's in the direction of the field, and the negative charge will feel a force opposite the direction of the field. And so if you can imagine those two, they are equal forces but in opposite directions. So we're not going to have any net left-right or up-down movement of this dipole, but we do have a net torque, as you can see. So we will tend to spin this, in this particular instance, in a clockwise fashion. And so soon enough, you would see the positive charge here and the negative charge here. They want to line up just like that. And if you remember what I said about the dipole moment vector a moment ago, no pun intended, it points from the negative to the positive. So that would be the direction of the moment vector. So oftentimes we summarize this by saying that the rotation of the dipole is such that its dipole moment vector wants to align with the electric field that makes it turn. And it's most stable in that position. So we often describe how much turning force or torque there is, and we often also ask, well, how stable is it? We use a measure of potential energy. So what the orientation that we started out in did not have the lowest potential energy, nor did it have the highest. But the orientation that I drew down here at the bottom, that would be the lowest potential energy that we could draw. We would call that U sub E. We use the symbol U for potential energy. The highest potential energy would be when I flip that thing completely around, kind of like my figure here on the left. If I were to take that dipole in that orientation and put it in the electric field, I could actually probably do that. Well, it's hidden. So that orientation would be the highest potential energy. So dipoles turn when you put them in electric fields. That's maybe a summary of what makes them interesting. So let's look at magnetic fields or magnetic dipoles. What makes a magnetic dipole? You might be surprised, but an easy way to make a magnetic dipole, they do occur naturally, but you can make a magnetic dipole just by taking a loop of wire and getting current to run through it. And so that's the figure here that I have on the left. We see a current. It's kind of hard to draw this. This all has to be in 3D, but you can kind of see this horizontal loop, and we've got this current running. And if I were to look from above, it would seem to be turning counterclockwise, that current. And it creates a magnetic field. Actually not too different than the electric field of the dipole, the electric dipole. If you kind of compare those two, see if I can get them in the same picture. Now they're not identical, of course, because electric fields start and end on charges, but magnetic fields have to go in complete loops. But there is a little bit of similarity between the two. So let's talk about how strong the magnetic field is due to a magnetic dipole. So this can actually be calculated from the Biot-Savart law. I'm not going to go through the whole calculation, but I will say that we're going to restrict ourselves to being on the axis of the dipole. So imagine, a line running right down through there, and somebody says, well, how strong is the field there? I'm going to write the equation here. So there's a dot there. If we're some distance z, I'm using z because this is oriented vertically, and we often call that the z-axis, then the B field can be written this way. 2 mu naught over 4 pi times pi r squared, where r is the radius of the loop of wire, times the current, all over z cubed. Now that's a big mess, and you might think, well, wait a minute, why are you writing a pi on the top and the bottom, and you've got a 2 on the top and a 4 on the bottom? That's a little strange. Well, there's actually a reason for that. And let me see if I can bring the other equation down and show you why. Okay, so here in red, I've written the on-axis electric field that I had above. You can go back and look and see that that's what I had. But I want you to see some things. First of all, we start with 2 times like the fundamental electrostatic constant. And that's exactly what this is. And then we have an r cubed in the bottom, where r is how far we are from the middle. And this is basically the same quantity also, except I just use z instead of r. That's sort of our variable. And then if you look at what's left over, in the numerator, we have what we know as the electric dipole moment quantity, the Qs. Well, there's a similar quantity here, and so maybe it'll make more sense that I tell you we call that the magnetic dipole moment quantity. And now I apologize for this, but in their infinite wisdom, the people who came up with this chose to use the Greek letter mu again. And this is not the same as mu naught. And I apologize for this, but mu is called the magnetic dipole moment vector, and it is equal to the area of the loop that's actually making the magnetic field. This in this case would be a circle, pi r squared, but this also works for squares and rectangles and triangles and any shape at all, as long as it's a closed shape. And then times the current that's running around whatever shape of wire that is. So that is the magnetic dipole moment vector. It also has a direction, just like we had to have a convention for the direction of an electric dipole moment vector. And of course, because it's magnetic fields, that convention must involve the right-hand rule. So if you curl your fingers in the direction of the current, then the magnetic dipole moment vector will go in the direction of your thumb. So in this picture here, it would be upwards. That also happens to be the same as the direction of the magnetic field, which is very convenient. So if you're doing one, you're kind of doing the other. So that's what a magnetic dipole is. It's a loop of current. Doesn't have to be a circle, could be any shape, with this magnetic dipole moment quantity, and we can calculate the field all around it. And now we'll get to what makes magnetic dipoles interesting. And the answer is basically the same as what makes electric dipoles interesting, and that is that they will twist and turn. If we take a loop of current and we place it inside another magnetic field, now just like we had to take our electric dipole and put it somewhere else where there's a field, like inside a capacitor, but we're going to take our magnetic dipole, our loop, and put it in something else's magnetic field. That something else is very often described as a solenoid, but you don't need to know that right now. Just know that we're in some magnetic field. And just like with electric fields, the dipole moment vector is most stable when it is aligned with the magnetic field that we put it in. So you see there on the left, that has the least stability, talking about this figure here, because the magnetic dipole moment vector is anti-parallel, or opposite the direction of the field that we placed it in. And if we give it a little bit of a nudge, it will very quickly flip around, and it will make itself in its most stable position. That's where it'll stay if it can. Now it might wobble back and forth, it depends on the situation, but it has the lowest energy or the most stability when the moment vector is lined up with the magnetic field. So this, in fact, is how we get a lot of things to turn. The very basis of an electric motor has to do with loops of wire. You often see big copper coils in a motor like that, and they're trying to line themselves up with some magnetic field. That's also why motors are very heavy, because there's usually a big heavy hunk of iron in there as part of it. So it's all about magnetic dipoles when you get the motors moving. So I'm going to leave it here, and I think I've hit just about everything I wanted to hit. And there is a lot more, of course, but I think this gives you a little summary, and I think 13.5 minutes is long enough. So I'll let you take it from here and find me or your teacher if you have more questions. Good luck.